never break. What I want to do today is continue my introduction to Einstein's theory of relativity. Last time I spoke a little bit about kind of the timing. 1905, 1915 is when Einstein developed his theory of relativity. The reading I assigned was chapter 23, A New Theory of Gravity. This is a tough read, so don't get too hung up on this. This is sort of a first stab at understanding Einstein's theory of relativity. What I want to do today is kind of give you an overview of it, what some of the assumptions are that go into it, and some of the kind of unusual or crazy sounding results that come out of Einstein's theory, okay? But before I jump into that, does anyone have any questions or thoughts before I start? Or anything administrative, schedule-wise that you need to ask me about? Okay, so Einstein's theory of relativity, as I mentioned, I'll write a few things on the board as I'm talking. So Einstein's theory of relativity, as I mentioned last time, he came up with it in 1905. Okay, so the special theory, which he came up with in 1905, eventually led to his general theory of relativity, which he came up with in 1915. And what it really did is it provided a new understanding of gravity, or what we had been calling gravity all along. Okay, so it's interesting that this notion of gravity has changed over time. Remember, the ancients talked about gravity, but they meant something very different than Newton meant by gravity. The ancients talked about rocks having gravity, right? So they have a gravitas, a tendency to fall they have kind of a nature to them that makes them fall. And air, on the other hand, has levity. It has a tendency to rise, okay? So that's how they were thinking about gravity. They weren't thinking of gravity as a force with which the earth is pulling on the rock. It's not like the earth was actually tugging on it. It's that rock has a natural tendency to descend, and that's what we meant by gravity in ancient and medieval times. Newton introduced a new concept of gravity. He said that what's actually happening is every mass pulls on every other mass. That's the Newtonian view of gravity. So it's sort of a force that's acting across space. This thing over here is pulling on this thing over here. Okay, so that's the idea of gravity that Newton had. And now we're going to see that the notion of gravity once again changes with Einstein. Okay, so in particular in Einstein's theory of gravity, so in the new, we would say, relativistic or Einsteinian theory of gravity, gravity isn't so much of a force as it is a tendency for things to move through space, but space is curved by the presence of masses. So in this new theory of gravity, what we call gravity is really understood as masses moving through space, or particularly through space which is itself curved or bent or deformed in some way due to the presence of masses. Okay, so I used the example last time of, imagine you have a mattress. This is a kind of a picture you can hold in your mind. It's not entirely a great analogy, but it works a little bit, I think. Imagine having a bowling ball sitting on your bed, right? And the bed kind of depresses underneath the bowling ball, so you got this kind of mass that's curving the mattress. And so if you were to put a tennis ball next to it, what happens is the tennis ball will kind of fall in toward the bowling ball. It's not because the bowling ball is attracting the tennis ball. Rather, it's because the mattress itself is curved, and this tennis ball tends to move along this mattress, and the mattress is bent. And so it kind of responds to that bending of the mattress. So you might imagine like you're rolling the tennis ball, and as you roll it past the bowling ball, it's going to kind of, its trajectory is going to deflect a little bit, and that's because the mattress itself is curved. Okay? So that's the kind of picture that one has in Einstein's theory of gravity, that these masses, any kind of mass that's in space, is in some way curving or bending space around it, and objects are moving in a straight line, you may say, through curved space. Okay, that's the idea that Einstein has. There's an equation, which you don't need to learn, but I'll just write it down just for effect here. The idea of Einstein's theory of gravity is that, I'll just write down the formula and then I'll explain what I mean by that. So 8 pi over c to the 4th times t, okay? And what does this mean? It says, and again, you don't have to memorize this, I just give you a sense of the way that Einstein actually wrote this formula down. On this side of the equation, you have a curvature of space. This g is meant to be in some way, it's supposed to capture the curvature of the space. These are some constants, including the speed of light, c, and some other numerical factors, 8 and pi. And then this t right here represents the presence of masses or energy. So presence of mass or energy. Okay? So the idea is this, Einstein wrote this equation down. How he got to that is a whole other issue. But the idea is on the right-hand side is sort of the cause, these masses or energy in space. And on the left-hand side is the effect. There's some curvature of space. There's a link between the structure of space and the masses that are present in space. Okay? That's what Einstein was trying to get at in his theory of relativity. Now let me remind you what Newton's theory of gravity, by way of contrast, was. So according to Newton's theory of gravity, which we talked about a bit earlier in this class, and we talked a lot about it in my Physics 201 class, Newton's theory of gravity basically said that when you have two masses like this, there's a force of attraction between them, right? This is mass 1 and this is mass 2. And this force that attracts them to each other, Newton wrote down force equals g m1 m2 over r squared, where r is the distance between them, and g is some constant of nature, the universal gravitational constant, and m1 and m2 are the masses, right? So that's kind of how Newton saw this. So that's one feature of Newton's theory of gravity. And another feature of Newton's theory of gravity, which isn't always explicitly stated, but Newton does explicitly state it in his Principia that he wrote in 1687, he believes that space and time and motion are absolute. What do I mean by this? What he claimed is that, let's suppose you wanted to measure the distance between two people, like, your friend standing next to you or sitting next to you. You could take a ruler and measure the distance between you and your friend, right? And every kind of measurement you do like that requires you to identify two different objects between which you're doing the measurement, right? So if you think about space, you've got two stars. You want to know the distance between the two stars. You can't do it unless there are actually two stars in space, right? So you're measuring the distance between two objects that are in space. But what Newton said is, even if you get rid of all those stars, you get rid of everything that populates space, one can still conceive of there being distances. So space is a real thing which is populated by masses. This is what I meant by absolute space. Even if you get rid of anything that you can use to measure distances between them, the concept of there being a space is still there. There's still this notion of space, even in the absence of anything in it. That's what he called absolute space. You might think of a huge grid system, right? And then when God created things, he started populating that space with stuff. But even if he didn't populate space, there would still be space, okay? That's Newton's notion of space. It's sort of an unchanging, immutable stage on which everything is placed. And even if there are no actors on the stage is still there, okay? Same with time. Newton said, well, anytime we do a measurement of time, we're using some object that's moving, like the sun rising and sun setting, right? So you're kind of looking at something that's repeating, and that's how we denote time. That's how we measure time. If you have a wristwatch, how do you denote time? It's by the angle that your hand has on your watch, okay? If you wanted to use a pendulum, you're kind of counting how many times the pendulum swings back and forth. So every time you actually want to measure time, you are using some clock that's a physical thing that you're watching. But he said, if you got rid of the sun rising and setting, you got rid of our watches, you got rid of pendulums, you got rid of any way that you could measure time, time would still be advancing. There's still this notion of absolute unchangeable time that events happen in, even if there aren't any events to measure. That's what Newton argued. He said there's a notion of time, an absolute time that's unchangeable, immutable, and things happen in it, but even if things don't happen, time is still progressing. Okay? Does that make sense so far? Okay? And if you accept this notion of there being an absolute space, kind of a stage, and an absolute time, then there's a such thing as absolute motion too. If something is moving through that space, it's truly in motion. And if it's at rest in that space, then it's truly at rest. So there's this notion of absolute quantities in Newtonian thinking. Okay? Now, how is that different than Einstein's theory? And what's the significance, or what's the relevance of this? What's the relevance of this? Well, in order to get to Einstein's theory, let me just point out some of the problems that Einstein pointed out with Newton's theory. Problems with Newton's theory of gravity. And these are a couple of things that Einstein points out in the reading that we have. The first problem that might occur to you is if all these objects in space are all attracting one another, you know, the sun is attracting the moon is attracting the earth, the stars are all attracting each other. If every mass attracts every other mass, then why hasn't the universe collapsed in on itself? Yet. Right? So if everything's attracting everything else, eventually it should sort of like be all attracting to some central point, and it should collapse in on itself. Okay? Yes?
Isn't that proved by the evolution of galaxies?
Okay, so
they're actually moving away from us.
Okay, so keep in mind that the redshift of galaxies, what we just talked about, Besto-Slipher, those measurements were done in the early 1900s, 1910, around then. Einstein came up with the theory of relativity in 1905. Okay, so the timing here is a little bit scrambled up. Einstein came up with this theory over a long period of time, 1905 to 1915. And this is the time when people were starting to do these measurements of the speed of the galaxies. And Slipher found out that the galaxies tended to be moving away from us. At least that's what the redshift implied. Okay. Before Slipher, there's different viewpoints on the universe. Okay. So in the ancient times and medieval times, there were different viewpoints as well. Remember Aristotle, who was not a Christian, he thought that the universe was everlasting. He thought it was always here and it always will be here. It's sort of this static universe, right? It always has been here, it always will be here. By the time people like Copernicus and Kepler and Galileo were around, they rejected that because they believed in the biblical account of creation. They said, we know God created the universe at a certain time, so it's not past infinite, right? So there was a creation event at some time. But by the time modern cosmology started coming around, there was sort of this belief that Christianity could be reconciled with science for many, many years. But with the 1800s, there started being a lot of pushback against the biblical account of creation. And so how does one understand the universe then for people who are going to reject a scriptural or biblical account, or for that matter, any mythology about a creation account? If people are going to reject that sort of thing, then a lot of them were going back to this Aristotelian idea and saying, well, maybe Aristotle was right. Maybe the universe has always been around. It's past infinite. And many people in the astronomical community in the 1800s, early 1900s had precisely this Aristotelian view. They basically went all the way back to Aristotle and said, we believe that the universe was past infinite, it never began. That way you don't have to deal with the pesky idea of how do we get here, right? As soon as you say, how did the universe begin? Well, it needs a cause, and then people start arguing, well, that was God. God created the universe, and so on. But if the universe was past infinite, if it didn't have a beginning, question solved, right? You don't need to have a creator if it's always been here, okay? So that's one of the reasons people really went all the way back to Aristotle and said, we don't need to have some kind of creator if the universe has always been here. But keep in mind, that raises precisely this question. If the universe is past infinite, it's been around forever, and we accept Newton's theory of gravity, that everything's attracting everything else, by now it should have collapsed in on itself, right? So that's the problem that's being raised here, and that's exactly what Einstein's bringing up. If the universe was past infinite, like Einstein believed also, and everything's attracting each other, then it should have fallen in on itself, and that's a problem with Newton's theory of gravity. There must be some problem with Newton's theory of gravity. Newton's theory of gravity must be corrected. That was the idea. Does that make sense? Do you understand how someone would come to that conclusion? Okay. So that's one problem. Another problem, as Einstein saw it, and this is kind of a philosophical problem also. I mean, all these have their scientific problems, but they raise these deeper philosophical or even theological issues, okay? But the other one is this. Einstein thought that we, and by we, I specifically mean our location, our frame of reference, our location here on Earth, or we might say our frame of reference, cannot be special or unique. Cannot be special or unique. There's no reason why our particular viewpoint should be more valid than any person or being that would be anywhere else in the universe. It's sort of a democratic principle. There's no viewpoint that's more elevated than any other viewpoint. Okay? It's sort of this democratic principle, and in particular, he thought that there can be no unique special reference frame. Can be or should not be any unique or special frame of reference. You know, it's interesting to see these ideas are very popular at this time as like kind of the spread of democracy and so on, right? This is the early 1900s. And also you see these ideas in science as well. There can't be any unique reference frame, any unique special frame of reference. So, you know, I don't think that's a causal relationship, but it's an interesting coincidence that those ideas are permeating in social sciences and in the natural sciences as well. Okay. And so, what does Einstein do? He comes up with his principle of relativity, which isn't really so much a new principle, but he just took it to its logical conclusions, you might say. Or someone might say extreme conclusion, logical conclusion, however you want to describe it. So Einstein's theory is based on what is called the principle of relativity. Principle of relativity. That's the foundation of Einstein's new theory. What is it? It basically has one assumption. It assumes that there is no way of determining whether you are at rest or whether you are in motion. There is no way of determining if you are truly at rest or truly in motion. Okay. So, and this kind of, there's some common sense recognition of this. So I don't know if you've ever ridden like an Amtrak train. I don't know if you've ever ridden a train. But I remember, you get on the train, you're sitting there waiting for it to start, you're looking out the window, and those trains start very slowly oftentimes, right? They kind of creep ahead slowly. And if you're looking out, you see the platform next to you, and it kind of feels like the platform's just moving backwards. You don't actually feel yourself moving forward. It's disoriented sometimes because you can't really tell whether you're moving or the platform's moving. And then you think, well, of course the train's moving, right? But you don't feel like you're moving. You feel like you're sitting still and the platform's moving backwards. And then your common sense comes in and says, well, of course the train's moving. But this takes that notion very seriously. It says this is what Einstein said, all of our perceptions of motion are always relative perceptions. I see, a tree going past me. Someone standing by the tree sees my car going past the tree. So what Einstein is doing here, he's saying, and this wasn't, like I said, unique to Einstein. He said, there is no principled way of determining who is truly in motion and who's truly at rest. You can always consider yourself to be at rest and everyone else to be moving. Okay? And to put a kind of a sharper point on this, he said, let's suppose, you go into the physics lab here at WLC, and you take a semester of physics classes, you shine lights on things and watch pendulums swing back and forth and collide carts and do chemistry experiments and whatnot. You do all these experiments in the lab, you get all these results, and from that you derive the laws of physics, right? You're a really good physics student, you find out all the laws of physics doing that in lab this semester. Now, what if you, instead of sitting in the lab here at WLC, you had a train car, pretty big one, right? And you brought all that lab equipment into this train car, and you shut all the windows, okay? And the train car was going at like 100 miles an hour down a nice straight railroad track for a really long distance. And you're really good at physics, so you can do experiments really fast while you're riding in the straight line down the track. What he's saying is if you did those experiments in this train car moving at 100 miles an hour, you would get the exact same results. You derive the same laws of physics in that moving train car as you did in the lab. So in other words, we would arrive at the same laws of physics if we were in motion going 100 miles an hour or we were sitting in the lab not moving at all. In fact, there's no way, he says, doing any kind of measurement of knowing whether you're truly at rest or truly in motion. Those are purely conventions. That's the claim. Okay, and again, this isn't to Einstein. You might remember when we read Copernicus, and he was actually citing Virgil, the poet, and he said, you see a ship going away, but on the ship they see the land going away, right? So this is something people had recognized. There's an ambiguity in the concept of motion. And so that's exactly what Einstein is doing here. He's saying, I'm going to take that very seriously. There's no way, literally no way of knowing if you're in motion or not. Okay? And he says in particular, and this is the thing that he took to, he worked out the conclusions is this, that no one had thought through quite as carefully as he did before this. He said, there's no way of knowing, even by measuring the speed of light. So there's no way of determining if you're truly at rest or in motion, no matter what experiment you do, no matter what science experiment you carry out. Even by measuring the speed of light. Why do I bring this up? Why is this, you can measure the speed of light in the laboratory. You take a laser beam and you shine it off a mirror and you kind of time how long it takes to get there and back. And you measure the distance and the time and you figure out how fast that light beam was moving. Okay? Yes?
It's assumed that light has a speed limit that it can't exceed. So if you were to measure that in different directions, you can then determine which way you're moving, if you're moving well.
Yes. Let me flesh that out a little bit. The reason why this particular experiment measuring the speed of light is perplexing, and this is something Einstein saw that other people didn't see. Think about it this way. I won't draw a picture. Yeah, I'll draw a picture in a minute. So let's suppose that I had a flashlight and I turned it on and it's shown in this direction. In principle, it might be hard to do it, but you could figure out, you could measure the speed of that beam. Okay? And the question is, if now I'm running in this direction and I turn on the light and we measure the speed of the beam, do you get the same measurement or not? And to kind of put a point on this, think about it this way. Let's suppose that I have a baseball instead. This is a more common example. I have a baseball, and let's suppose I throw the baseball in this direction, and somehow you're to measure the speed of that baseball. Let's say I have a really good arm and I can throw it like 60 miles an hour. I can't, but whatever. Suppose I could. You can measure the speed of that baseball to be 60 miles per hour. Now, if I got in a pickup truck and stood in the back of the pickup truck, and the pickup truck was going 60 miles an hour this way, and I stood in the back and I threw the baseball, and you measured the speed of that baseball compared to you, how fast would that baseball be going compared to you? 120, right? You add the speed of the pickup truck to the speed of the baseball, and that's how you get the speed of the baseball compared to you, right? So if you think about, I'll draw that. So you've got this pickup truck right here, okay? And me in the back right here, and I can throw this baseball, and I can throw it at 60 miles per hour compared to myself. But if the truck itself was going at 60 miles per hour, and you were watching, you were standing on the ground watching this, you would measure, or if the baseball hit you or your glove or something, it would come at you with 120 miles an hour of speed, right? Why is that? Because you add the speed of the truck to the speed of the baseball. This is common sense. This is what we do all the time. Okay, this is how you do these kinds of calculations. People were well aware of this. We're well aware of this. There's nothing controversial about this. Here is the perplexing thing. Let's suppose now you get in the back of the truck, and instead of a baseball, you have a flashlight. And you turn on the flashlight. And we all know, people have measured this since the mid-1800s. In fact, the 1600s, to less accuracy, but the 1800s with the work of Fizeau. This travels at about 300,000 kilometers per second. That's the speed of light. That's the speed that it comes out of that flashlight. Okay? So if someone were standing on the ground right here, and the truck wasn't moving, they would measure 300,000 kilometers per second of the speed, and so would you standing in the back of the truck. Now, probably see where I'm going with this. What if the truck is driving forward at a high speed? 60 miles an hour, 100 miles an hour. Let's say really fast. Let's say 100,000 miles an hour. Okay, some huge speed. And just to make our calculations easier, let's suppose the truck, I know this is absurd, but imagine this. Let's suppose the truck was going at 100,000 kilometers per second. It's like a spaceship, okay? It's going really fast. The question is, how fast would the person on the ground see the light coming toward them? What do you think? Yes?
It'd still be 300,000.
Does that sound bizarre? Okay, so notice what's happening is if we say the speed of light is a constant, which everybody says, speed of light is constant. And by that they mean the same for all observers. That means that both you, in the back of the truck, see it moving away from you at 300,000 kilometers per second, and the person on the ground sees it coming toward them at 300,000 kilometers per second. And you're both right. Despite the fact that you've got the flashlight on a truck going at 100,000 kilometers per second. That's weird, okay? That's bizarre. That's the implication of saying the speed of light is a constant. It's one thing to say that, it's another thing to understand the implications of that. The implications is that both of these people measure the same speed of light, despite the fact that the source of light is in motion compared to the other one. We don't do that for anything else. We don't say the baseball flies at 60 miles an hour toward him and 60 miles an hour away from him, even though the truck is going at 60 miles an hour. If you find this counterintuitive and strange, you're thinking about it correctly. That's exactly what Einstein's theory of relativity is claiming. The speed of light is a law of physics. There's no way you should get the same measurement regardless of your state of motion. That's what he's claiming. Yeah.
What about sound? Does that work the same way?
Sound is a little bit different because sound travels through air and you're moving through the air. Here, we're imagining this is in a vacuum. There's a little bit of a caveat here. And the speed of light is a constant in a vacuum. Everybody at this point knew that the speed of light slows down when you go into like glass or water. That's why it bends. So to kind of simplify the discussion, and we can debate about this, but to simplify the discussion, to get rid of the complication of these like media, like glass, water, and so on, just imagine this going on in a vacuum. Okay, you pump all the air out of the region. The speed of light is going to be the same for this person and that person when you measure it in a vacuum. Okay, so in a vacuum. Okay. That's what the claim is. Yes?
Does it slow down when it hits air, or does it just move differently?
When it hits air?
Or glass, or...
It does. Actually, the speed of light changes when it goes from one medium into another. Yep.
How drastic?
Well, the speed of light in glass is about 2/3 of what it is in a vacuum. So about 200,000 kilometers per second. Okay. But everything we're saying here, it gets complicated when you start talking about in different media. So just to avoid that, let's imagine we're doing everything in a vacuum. This is still really, really weird, right? That's the claim. Now, if you're going to claim that the speed of light, as Einstein claimed, the speed of light is an absolute. You would say absolute. It's the same for everybody no matter what. What's going to end up happening in Einstein's theory is if the speed of light is absolute, then you have to start playing with the notion of space and time. So in Einstein's theory of relativity, the speed of light is an absolute, and space and time become flexible concepts. It's different than in Newton's theory. In Newton's theory, space and time are absolute, the same for everybody, and the speed of light is something that is different for different people. So in a sense, they're both theories of relativity, and they're both theories of something being absolute. They just disagree about what's absolute and what's relative, right? So Newton takes our common sense notions of space and time to be correct, that they're absolute things. Distance from here to here is the distance from here to here. The time between two events is the time between two events. It's an absolute space, absolute time theory. And as a result, the speed of light would have to be different for different observers. Einstein turns that whole thing around. He says the speed of light is a thing that's absolute, the same for everybody. And now we've got to have flexible ideas of space and time. Okay? So it could have been called the theory of the absolute speed of light instead of the theory of relativity. Okay? That's another way of thinking about it. Okay? Questions up until this point? Again, I'm just sort of telling you how this is playing out, right? Yes.
So does he say that there's nothing that can exceed the speed of light?
Yes. Nothing can exceed the speed of light. There's nothing that can go faster than light, according to this theory. Yep.
So if you were to take this theory seriously, then you would say that not even supernatural things can travel faster than light?
One would have to define what one means by supernatural then. But anything, there is nothing according to this theory that can go faster than the speed of light. Okay?
Okay.
This is why, by the way, I'll say one thing about this, but I won't go too far into this. Einstein had a lot of problems with quantum theory, quantum mechanics. He didn't like it at all. He disagreed with it until his dying day. Okay? And part of the reason is because quantum mechanics seems to suggest that something over here can affect something over here faster than can be communicated by light traveling at its speed. So it seemed to be non-local interactions or instantaneous, what he called action at a distance, which he didn't like, because the speed of light is a speed limit. So something over here cannot affect something over here without the time elapsing for light to get from here to there. So there seemed to be some kind of inherent problem between his theory of relativity and quantum mechanics. Okay. Now, this is the assumption of the theory of relativity, that you can't know if you're at rest or in motion, and in particular, you can't do any science experiment to determine if you're at rest or in motion. And most importantly, by measuring the speed of light, you can't tell if you're at rest or you're in motion, because the speed of light is the same for everybody. Okay. Now, what are the consequences of accepting Einstein's postulate of relativity? Consequences of accepting Einstein's postulate, or I might say axiom or starting point of the principle of relativity. You know, it's a pretty simple assumption. And now let's just talk about what are the logical implications of this. Like I said, first of all, the speed of light, being one of the laws of nature, is the same for everyone. Being one of the laws of physics is the same for all observers. Same for all observers, even if the source of light is moving compared to you. Right, so if someone throws a flashlight and has it turn on while it's flying through the air, you don't add the speed of the flashlight to the speed of the light to get the new speed of the light. Okay? A second consequence is that there's no such thing as absolute time. There is no such thing as absolute time. Einstein read Newton's Principia from 1700. He read what Newton said about it and that there's this absolute time. And Einstein said, that's bogus. There's no such thing as absolute time. Newton was wrong about that. All of our measurements are of the relative time between things, and there's no way of getting outside of that and saying there's some absolute reference frame of time. Okay? And so time becomes a fluid kind of concept. But by fluid, I don't mean anybody can say whatever they want about time and they're right. He came up with these laws that basically connected the time interval between events as measured by one set of people to the time intervals between the same events as measured by another set of people. So kind of he came up with equations that kind of connected different reference frames. Okay, so let me give you an example of what I'm talking about. So you have to understand the concept of what we mean by an event. Okay, so like I snap my fingers, that's an event, not a very exciting one, right? But that's an event. It's happening at a particular location here in S105, 109, what are we in? Okay, this room. It's at a particular location at a particular time. So there's kind of four coordinates, an X coordinate, Y coordinate, Z coordinate. Those are the spatial location of my finger. And then the time coordinate, when it happened. So if you specify four numbers, X, Y, Z, and T, you can specify that event. Then I have this one. That also is an event. It happened at a slightly different X, Y, and Z, a slightly different spatial location, and at a later time. So I go like this and this. I have two events, and they're separated by a certain amount of time. There's a temporal difference between those two. And what is the difference in time? Well, I look at my watch and I say this one happens, and then this one happens 1 second later. Okay, good so far? Now, what Einstein's theory claims is that we sitting in the room, we're all sitting here together, we'll agree that this event happened, then this event happened. But if there were some other observers who are traveling by us at a very high speed on like a train or something, at a really high speed, they might measure these two events to happen simultaneously. And another set of observers who are all riding on a train at maybe a higher speed would see this event happen first and then this event. So the temporal difference between two events can be different for different sets of observers who are in motion relative to one another. If that again sounds weird, you're thinking about it correctly. Okay? So the temporal separation of two events, or maybe I'll say it this way, events that are simultaneous to one set of observers, like us in the room, are not simultaneous to another set of observers who are in motion compared to the first. Now, when you hear a statement like that, you think, okay, right. But come on. Like, either this happened first and this happened second, or they happened at the same time, or this happened first and this happened second. There is a true order of those events, and one of us is right and the other people are wrong. Maybe the other people are deceived, they're having an illusion, there's some weird thing going on, but there's got to be an actual ordering of those events. Newton would say, that's correct. There's an absolute time, and in that absolute time, this one really happened first, this one really happened second, and anyone who says different is sort of suffering from some illusion, some delusion, there's something weird going on there. Newton puts it this way, he says, no, there's no notion of absolute time, there's no true ordering of those events, and moreover, you can't tell which set of observers are right. Why not? Because each set of observers can perceive themselves to be at rest. There's no set of observers who's truly in motion, no set of observers who's truly at rest. They all consider themselves to be at rest and the other persons to be moving. So there's no principled way of distinguishing who's truly at rest and truly in motion. And if you're going to say these events, there's some preferred reference frame, the real reference frame, in which this one really happened first and this one really happened second, you're misguided because there's no way of knowing who's right. Okay? That's the implication of this. That's what he's saying. Okay? Yes?
Wouldn't that have some problems for logic?
Absolutely it does. Why do you say that?
Well, because if I say the statement, the right hand stacked before the left hand, and assuming we have some way to refer to one absolutely and not relative to a position, then that statement would either be true or false. But with this, it would neither be true or false, which would break one of the established presuppositions of logic.
Okay, so this, and what you're saying is that something cannot be before another thing and to be after another thing. Like that's logically inconsistent, is what you're saying, right? You can't make a statement, A happened first, then B, and another person say B happened first and then A. They cannot both be right.
Yes.
That's what you're saying.
The proposition cannot be both true and false.
Correct. So the way that Einstein and relativists will explain this is they'll say the notion of first and second is an ambiguous notion because time is an ambiguous concept. So you're kind of, you're equivocating on what you mean by first and second. That's how they would approach this. They would almost treat it like a semantic problem with how we're defining first and second. Okay. I think there are other problems with it, but the one you're bringing up, that's the way that it would be addressed. Okay. Good so far. We have like 3 or 4 minutes. Let me get through a couple of other things here. So no such thing as absolute time. Events that are simultaneous to one set of observers are not to another set of observers. Another one is what is called time dilation. And this is kind of a famous one about people in motion, time flowing at different rates for different people who are in motion compared to each other. So put it this way, a simple way, my watch ticks once every second. Okay? You're sitting here next to me and your watch is ticking once every second. We can synchronize our watches and so that all of our watches are all ticking once every second. We all agree that they're ticking at the same rate. And we're using these ticks as kind of an indicator of how fast time is advancing. Now, what Einstein's theory of relativity says is that I take my same watch that we just synchronized, and now if I run past you at some very high speed, it has to be a really high speed to have a pronounced effect. But let's just suppose I can go at some really high speed, like half the speed of light. That being the case, when you look at your watch and you look at my watch, they will no longer be ticking at the same rate. In particular, you will see my watch ticking more slowly than your watch, which is identical to mine in every other respect, except mine's going past you. That's called time dilation, or in particular, moving clocks. Moving clocks are seen to tick slowly. And by slowly, I mean more slowly than an identical clock that's at rest. Okay? Now, you might say, well, okay, your clock, because Dr. Kuehn, you're running past, your clock is ticking slowly, mine's the right one. Yours is obviously, there's some weird problem, I don't know what it is. But remember that I'm at rest compared to my watch, and so I think mine is right, and yours is wrong. And there's no way of saying, and here's that caveat once again, there's no way of saying who's truly at rest and who's truly in motion. So there's no way of, in principle, saying which one is correct. So all this always goes back to this notion of you can't tell who's in motion and who's at rest. There's no way of distinguishing whether you're in a state of motion or a state of rest. That's the assumption, and it plays out in all these kind of funny ways throughout the theory of relativity. Yes?
But both clocks still are ticking at the same rate. It's just loosely that.
Okay, so that's a way of trying to describe it, but keep in mind what you're saying is that, well, it's just an illusion that you seem to think it's ticking slowly.
Yeah.
But Einstein's theory of relativity would say this, it would say there's no distinction. What appears to you, what you measure is what you measure.
Right.
And when you say it's an illusion, you're assuming that there's something else that is the truth and you're mistaken. Okay? And the theory of relativity says, no, there's no truth to which you can compare it. Your measurement is your measurement, and the time is ticking differently for different observers, and hence time flows differently for different people. Okay? Again, when people hear this, they usually, first of all, are confused. Second of all, they're angry. Third of all, there's like denial. There's like the stages of grief or something, whatever. And then there's acceptance or whatever. So anyway, so that's a quick introduction to some of the aspects of Einstein's theory of relativity. And I hope you have a nice Thanksgiving. I'll see you when we get back next week.